Hi, Alexa here. Did you know you can use Opto 22's Intelligent Snap I/O as remote I/O with an Allen Bradley RSLogix based controller? It's true, and Snap I/O handles I/O functions remotely, freeing up your controller for other tasks. Perhaps best of all, no programming is required, just simple configuration. In this first of a 4-part series of videos, I'll show you how easy it is to get data from Snap I/O into an Allen Bradley PLC. For all 4 videos, we'll be using this demo unit. We've got an Allen Bradley controller and a Snap I/O unit with a SnapPack EB1 brain and assorted I/O modules. Both are connected to a managed switch. Let's get started. Here's the Ethernet IP Configurator, a free utility from Opto 22 that we'll use to configure our Snap I/O. The Snap brain I'm using for this demo doesn't have an IP address yet, so its MAC address is listed under Discovered Devices over here in the device tree. You can find the Snap I/O's MAC address listed on a label on the outside of the brain. To assign an IP address, I'll double-click the MAC address and type in the IP address that I want to use. I'll also enter the subnet mask that I'm using for all devices on the network. I'll click OK. And now I can give my I/O unit a more meaningful name, such as Snap Intelligent Remote I/O. Now, the Snap brain takes care of temperature conversions and even thermocouple linearizations. I'll just choose to have temperatures displayed in degrees Fahrenheit. For now, I'll leave the watchdog and click OK. My brain appears over here in the list. I don't need this unnamed device, so I'll go ahead and delete it. Now that we've configured our brain, we need to configure the modules on the rack. For this screencast, I'll configure 3 modules and an I/O point on each one. I've got a discrete or digital input on the first slot, so I'll select this module and double-click on it. It's a digital input, and the module is an IDC5D. I'll click OK. If I click on the plus sign, I see 4 points listed because this module can handle 4 channels of I/O. On the last channel, I've got a photosensor wired, so I'll name this point photosensor and click OK. The next module on my I/O unit is a digital output, so I'll select digital output and ODC5 source and click OK. Expanding this folder, I've got an outside light wired to the last channel on the module, so I'll name this point outside light and click OK. Let's do one more point. This time it's a thermocouple module in the 06 position. I'll double-click the module. It's an analog input, and the module is an AITM. I'll click OK. Expanding this folder, I'll see the module accepts up to 2 thermocouple modules. I've got one wired to the first position, and I'll name it room temperature. In the module field, I'll select Type J thermocouple to match the thermocouple wired to the module. Because we selected degrees F when we configured the brain, the temperature readings will be converted to degrees Fahrenheit. This means you won't need to do any thermocouple linearization at the PLC level. The Snap I/O brain automatically converts millivolt values into temperature values. Let's move on and create our assembly instances. Snap brains support both implicit and explicit messaging. We're going to focus on implicit or I/O messaging. Implicit messages are predefined and therefore fast and efficient. Using the tools in the Configure Assemblies tab, we'll specify what information is sent between the Snap I/O and the Logix controller. These implicit messages are called assembly instances. Typically, each Snap I/O unit will have 2 assembly instances, one for input to the Logix controller and one for outputs from the Logix controller. Let's configure assembly instance 100 to be our input instance. Our ultimate goal here is to read in the value of the photosensor and, depending on the value, turn on or off the outside light. We also want to know what the temperature is in the room. So the input instance will handle reading the photosensor and the room temperature. I'll go ahead and click Add. To get the photosensor, I'll select Discrete Input Point. I could specify the module and point number, but it's much easier to select point name and then choose my point. Under Attribute, I'll make sure Value is selected and I'll click OK. Now, the status of a discrete input only takes 1 bit, but the generic Ethernet module that we'll be using in RSLogix expects the SnapIO brain to send data in packets of 32-bit words. I've only got 1 bit, so using my higher math skills, we can deduce that we need a padding of 31 bits to get that total of 32. So I'll click Add, select Pad, and type in 31. Let's add one more data item. So we'll add to this input instance, and we'll select Analog Input Point. The point name is our thermocouple, the room temperature. Over here under Attributes, we have a lot of choices of data that we can specify. For example, for this analog input point, we could select value, which will give us the reading in counts, but I'll choose R value, which will give us the reading in our specified engineering units. For now, let's click OK. We're asked if we would like to fill in the rest of the module with the same type of point. This is useful if I was adding assembly members of the same type from the same module, but I don't have any other thermocouples, so I'll just click OK. The size of the R value is 32 bits, so we don't need to add any padding here. Well, that takes care of our inputs. Now let's create an output instance using assembly instance 101. I'll click Add and select Discrete Output Point. I'll choose my outside light under the point name. Make sure Value is selected under Attribute and click OK. Once again, the size of this information only takes 1 bit, so we need to add a padding of 31 bits. I'll click OK. Now that I'm done building my instances, I'll go to the Verify tab. This screen summarizes what we've built. For our input assembly instance 100, we have 2 dints. For our output assembly instance 101, we have 1 dint. We also see that we've properly configured all of our assembly instances. If we had forgotten the padding or used the wrong number of bits, for example, we would have gotten an error. Next, we need to send this configuration to the Snap Brain to establish I/O messaging capabilities. I'll click Download. We see the Snap I/O listed here. I'll click on the IP address and click Download. Ethernet IP Configurator transfers the configuration file to the flash memory of the Snap I/O. It also lets us know there are other unconfigured modules on the rack, but we'll save those for another screencast. I'll close the screen. At this point, it might not be a bad idea to save our work, so I'll click on the Save icon, type in a name, and click Save. Now we've seen how to use Ethernet IP Configurator to manage and configure Opto 22 hardware. We're ready to move on to RSLogix and see how easy it is to add and communicate with our intelligent remote I/O. Here in RSLogix 5000, I'll create a new project by selecting File New. I'm using an Allen Bradley CompactLogix PLC, and the model type is listed here. I'll give it a name by typing IO4AB and clicking OK. The controller, IO4AB, is now listed in the tree on the left. Now we need to add the Snap I/O. Under I/O Configuration, I'll right-click on Ethernet and select New Module. I'll expand the Communications folder and scroll down to select the generic Ethernet module. Once I click OK, I can then name my I/O. Remember, we called it the Snap Intelligent Remote I/O. And I'll verify that the COM format specified is data dint. I'll enter the IP address of my Snap I/O, and then I'll come over here to Connection Parameters. We need to match up the data with what we created in the Ethernet IP Configurator. Our input instance was 100, and we created 2 32-bit words. The output instance was 101, and we created just 1 32-bit word. We're not using the configuration instance, but I have to put something there, so I'll type 102 and click OK. From here, I can change the RPI time. By default, implicit messages will be sent every 10 milliseconds. I'll click OK, and we're ready to try it out. I'll click Download, and Yes to run it. Let's take a look at the controller tags. I'll expand these folders to look at my input data. The first bit is my photo sensor, so I'll type that in the description. Now I'll flip the switch representing the photo sensor on my load panel, and the value changes. See how quickly we establish communications to our I/O? The next item is the room temperature, so I'll go ahead and put a label in that description field. Fortunately for me, it's not really that hot in here. It's just that the data is displayed as a DINT rather than a real or floating point number. We'll deal with that shortly. Just note for now, if I place my fingers over the thermocouple, the value does increase. Now let's take a look at the output data. I'll expand all of these folders and scroll down a bit. The first bit is our outside light, so I'll put that in the description. Here's the cool part. If I type a 1 in here and hit enter, the outside light turns on. If I type a 0 and hit enter, the outside light turns off. But as cool as that is, the goal is to have some code where the photo sensor controls the outside light. So let's go offline and write the ladder logic code that will do that. We'll go to the main routine. On this first rung, I'll add a normally open contact. I'll specify our photo sensor, which is located on our input instance, specifically on bit 0. Next, I'll add an output coil, and we'll specify our outside light. That's located on the output instance, specifically bit 0. With this code, the photo sensor will now trigger the outside light. Now let's deal with our temperature reading. The thermocouple value was already linearized by the I/O, but we want the temperature displayed as a float or real. I need to create a tag to store the data, so I'll right-click on Controller Tags and select New Tag. In the name field, I'll type room temperature, and for the data type, I'll browse to select real. I'll click OK, and I'll click OK again. Back in the main routine, I'll add another rung, as well as a CPS instruction. The source will be our thermocouple, which is on our input instance. I'll select it here. The destination will be that room temperature tag that we just created. And the length of the data will be 32 bits. Think it'll work? Only one way to find out. Let's download the program. I'll click Download, and I'll click Yes. To test it, I'll toggle the photo sensor switch, and indeed the outside light is triggered by the photo sensor. Let's take a look at the tags. Here in room temperature, I can see a meaningful value in degrees Fahrenheit. Again, if I put my fingers over the thermocouple, I see the temperature increase. So if you made it to the end of this video, thanks. I hope it was helpful in showing you how easy it is to establish communications between an Allen Bradley PLC and Opto 22's remote Snap I/O. Stay tuned for future screencasts that show you how to take advantage of the intelligence of the Snap I/O system. See you next time!